Okay, let's get started. Welcome everyone. Thanks for stopping by to the show. How's Dublin been so far? Good. It's my first time here. I'm here with my family, so it's having a great time. So today our talk is centered around geo-distributed storage for Hadoop. In short, what that means is HDFS, as you guys know it, is primarily a single site storage system, right? It's great to run in one data center. A Hadoop cluster exists in one data center. It's great at running commodity storage and analysis there. But we will talk about some problems and challenges where there is need to take this across the globe, right? So we're gonna take Hadoop across the globe. Quick introductions. I am Nikhil Joshi. I've been a product manager with EMC for about 2 years now. Before that, I was an engineer at Yahoo, Pivotal, Informatica, and a few other companies. So I have some Hadoop experience. Before I came in here, I was doing a Pivotal Hadoop distribution at Pivotal. And my colleague Vishrut Shah.
Hello, everyone. It's good to be here, and thanks for showing up for our talk. I primarily am an engineer working on the engineering side for ECS at EMC. I joined EMC 3 years back mainly for this product. A bunch of us from Microsoft moved over and started this product in the Seattle office of EMC. And ever since then, till today, I've been working on this product, and it's been a great journey so far. I'll be glad to share some of those insights about what our product has been through the journey so far, and give you an insight on what we have done in the world of Hadoop and geo-distributed active, and some of those cool things. So Nikhil here is going to get started and walk you through what we have here and what are the problems we are trying to solve and how we are trying to solve it. And after that, I'll take over and show you guys some of the things in action on how we have solved an actual real use case using the ECS system for geo-distribution. Before I forget, we have a headset to give away by the end of this talk. Usually people give it away by raffles. We at ECS or EMC in this particular group have a tradition of giving it away to the best question we get or the worst question we get on how you want to see it. Also, there are some USB drives we left on the front 2 rows, so feel free to grab them now or later. Over to you.
Cool. Thank you. All right, so show of hands. How many of you have Hadoop clusters in production? More than one? That's great to see. More than one across geographies in 2 data centers? Okay, beautiful. All right. So this is nothing to write home about, but most Platform 3 apps, as IDC calls it, or cloud apps are global these days, right? Data is generated all across the world. It's ingested in data centers in California, in Asia, etc. But analytics as it exists today via Hadoop is primarily a single site concept, right? You run Hadoop analytics on the HDFS in a particular cluster. So this limitation is kind of very limiting because what customers resort to, the customers EMC speaks to, is doing dist copy across data centers. Anybody knows what dist CP is? Great, right? So you know the problems that come with dist CP. It's a active-passive configuration, extremely hard to scale beyond 2 sites. It uses resources on the cluster of the primary site. And it's a periodic transfer. It's not synchronous, so you write a file on site 1, only when dist CP kicks in the next time, it shows up on site 2, right? So Hadoop, I think vendors have done a great job to set up your first Hadoop cluster and run a word count job really well, right? Ambari can do it in a second, Cloudera Manager can do it in half a second. But what beyond that? We have been speaking to most of EMC's customers are large enterprises or service providers. A large European bank we spoke to in December had this problem. So their workflow included a real-time analytics or a stream analytics engine, which takes in ATM data, transaction logs from their websites, mobile phone applications to do some fraud analysis. After the stream processing, the data was explicitly copied over to a what they call a risk analytics infrastructure, which is a bigger Hadoop cluster capable of running batch analytics, and they do it by disk CP, and they run their batch analytics there. Further on, the same data set is moved to cold archive for compliance. This is a cheaper tier of storage, which is cheaper than HDFS commodity hardware, right? Now, the scale that these guys face is like this, right? This is not your childhood data center Hadoop cluster anymore. It's 3 data centers, 7 unique tenants, ingestion of 200 GB a day, and this is what blew our mind, right? They have 27 Hadoop clusters in production across test and dev and production and DR. And none of this is under centralized IT control. Development teams, business units spin up their own Hadoop clusters, they run their analytics, they shrink, they resize their clusters, and all this is in a vacuum, underutilization of resources and silos. So how do we get over this problem, right? What EMC has envisioned is a centralization of the data silos in your enterprise. A way to bring all of your enterprise's data across geographies into a single unified namespace, so your entire enterprise sees one corpus of data. And on top of this, each business unit as a service or as a Hadoop as a service offering spins up Hadoop clusters of their choice, of their size, and reach out into this enterprise data lake to analyze the data. So some desirable characteristics of such a geo-distributed storage system is that it needs to be Hadoop ready. What that means in layman's terms is it needs to be a Hadoop API compatible storage system. So say you have this storage system which holds like petabytes of data. To analyze it, you need it to talk HDFS, to run a pig script against it or a Hive query against it. Most Platform 3 apps or cloud apps are also polyglot. What I mean by that is a mobile phone application usually wouldn't do an HDFS put. It would use an S3 API or an OpenStack Swift API to upload data in and out. There are NFS based systems. So the data ingestion mechanisms are not HDFS only or S3 only. They're usually a mix of this. So it needs to speak multiple languages. And 3x replication across geographies won't do anymore. HDFS did a great job with 3x replication in a single site. Now you move it to 3 sites, it's suddenly 9 copies of the same data, right? It's just not scalable. So some smart mechanisms to protect to compress or protect your data in a non-linear fashion. It needs to be WAN efficient, as in because these are across geographies, you cannot have a latency hit of every data block going to all the sites in your network. Active, and strong consistency are something very important, especially in the healthcare and financial verticals. A file written in California needs to be immediately read in Sweden without actually sticking to the eventual consistency mechanisms, right? So if you have a analytics infrastructure where you are relying on data ingestion from various data centers, strong consistency semantics are very important. And also to make sure that your resource utilization stays high, unlike a disk CP based configuration with an active passive data center, both centers need to be active and usable at the same time. So what is ECS? ECS is Elastic Cloud Storage. It is a petabyte scale, scale out object storage engine. Think of it as Amazon S3 on your premises, right? You can tie in data centers from various enterprise locations, geo-distribute data across these various data centers, have them accessible in an active fashion across all data centers with strong consistency semantics. This is what ECS does very well. Now, on top of this infrastructure comes a global namespace. So this is what I say. Instead of having a HDFS cluster on every node, you can project a global namespace to your applications, and all your applications can choose various semantics to ingest data and to read data out. So this could be Swift, HDFS API, S3, HDFS, Swift, and NFS. On top of these sit your apps which read, write data or do analytics using Spark or regular Hadoop clusters. Now, all this infrastructure is strongly consistent, available actively with geocaching schemes, which based on read patterns of the data, caches it at the appropriate site. So say though data was ingested on a site in Paris, if your applications, if your mobile application, most of reads are happening here, the data is cached over this website, over this data center. Any questions so far? Yeah.
Have you taken into account possible jurisdiction limitations? For example, we have a cluster in China,
Yeah.
which the government doesn't allow its data to.
Okay. Great question. So this is a little bit of a misnomer. When I say geo-distributed data, not everything in your storage system is distributed. We allow what is called selective replication. As you know, Amazon S3 lets you create buckets of data, right? So similarly, ECS also lets you create buckets of data, and for each bucket of data, you can choose your replication. So a bucket of data, bucket 1 could be replicated only between Beijing and Paris, bucket 2 could be replicated across 3 sites, and bucket 3 could be only confined to Denver. Yes?
When you now define such a bucket, can you say, all right, I want one copy of the bucket all the time being in country A, and the rest I don't care, so that you can do a disaster recovery systems saying, all right, I have always in this location all data.
Right, yes, you absolutely can do that. So there are 2 schemes of replication grouping, right? One scheme is where I say that my data is replicated between Paris and Beijing, but is replicated between all 3 sites, but I only have enough copies on the other 2 sites to survive a disaster. That's one scheme. So if this data center goes down, I can recover my data using the data on the other 2 sites. But the second scheme is where I can pin one copy of data in each data center. You see what I'm saying? So a file here will also be here and also be there. So that prevents against disaster recovery. That prevents protects you against disasters, but also makes your data available to your apps in every location.
So for failover disaster recovery, you can also say I take 4 times replication in Hadoop, 2 in country A, 2 in country B, and then I have double data, secure data in 2 data centers.
Partially.
Sorry. So what ECS does is the geo replication or the geo distribution which you see here is mainly a protocol or algorithm driven by ECS, and it makes a lot of effort to reduce your storage overhead. So it's not really, let's say you have a 10 GB object, right? It's not really that you have 10 and 10, 20 or 10 and 10 and 10 as 30 GB when you do geo replication. In fact, with ECS, the higher the number of sites, the lower your storage overhead gets. So it's not a simple multiplication here. Usually our storage overhead is less than 3 times. And once you increase the number of sites, there is a possibility of even reducing less than 2 times and getting geo-replication in a way that you can handle one zone or one site completely going out of the picture.
Yeah. We do some mathematical calculations like erasure coding and XORing of the erasure coded chunks to bring down the level.
Yeah.
Is it possible to implement a scenario in which I would want to have, let's say, a number of regional subclusters on every continent, for example, and make sure that there is a copy of any data within the cluster on each of those regional subclusters?
Yeah, so if each of your regional data centers, as you call them, is set up as a different virtual data center or a different zone in ECS, you can set up a scheme where each of your regions have a copy of the data. So that might be beneficial or harmful to your use case depending on what storage efficiency you want, right? If you having it pinned to every site will increase the storage overhead.
Of course, yeah. But on the other hand,
What is the global architecture? Are there autonomous storage appliance?
Yeah.
Yeah. So on any location, I can set up my own policy.
Replication policy, you mean?
Yeah, replication policy.
So no. So the way it works is this can be an appliance or a commodity server, and each of the failures, the monitoring is done individually on every site. What is actually global is your replication policy. So the replication policy is defined at a global level. But at an individual level, you can control how many servers you have, what happens when the disk is down, what happens when a server is down.
Because right now, up to now, we're just talking about disaster recovery. This is one point.
Yeah.
But there is another side of disaster recovery is data corruption. So I also want to work on this data corruption.
So data corruption is handled locally in the sites.
Yeah.
So our algorithms make sure that during corruption, we don't have to go across the WAN to fetch your data.
What are the preconditions for the global namespace? Does it require a global master data metadata management between the countries?
Yeah, we haven't gone into that detail yet, but the way ECS is built is that both the data and the metadata in the system are stored in the same way. Unlike HDFS, where there is a name node server which spews out metadata and the data nodes which spew out the actual data, the architecture with ECS is completely different. So assume you have 10 ECS nodes, you can hit any ECS node and ask it for a metadata report, like how many blocks are there in your file. You can also ask it to fetch the blocks. So there is no name node concept in ECS.
My question is related. You said replication is synchronous?
Yeah, no, I did not say that. So I said that.
And I misunderstand you, sorry.
Yeah. So the system is strongly consistent. The replication is not synchronous. When I put data here, we ensure that the metadata of that is replicated synchronously. So all data centers know that, hey guys, a new file has been dropped into Paris. Beware. Right? Okay, cool.
Global namespace, is it dependent on DNS?
Global namespace is depending on the.
Global namespace, in my opinion, means that a client, wherever he sits all over the world,
Yes.
is getting to his namespace.
Oh.
So to say.
Right. So a global namespace is not defined by a single IP address like aws.amazon.com. You could potentially do that with a global load balancer, but we don't give it out of the box. Our endpoints become endpoints in the server. So if your mobile application, if your web server is close to Paris, you talk to the Paris data center while still being able to see the global namespace or the global data view.
But in the case that Paris data center is away,
Yeah.
you have to fail over manually.
The storage is not, you don't have to fail over manually, right? The bucket of data that you lost in Paris is available, replicated and recovered in the other two sites. What you will have to fail over are your applications. So if your Hadoop cluster is talking to the storage on this data center and this data center dies, the Hadoop cluster will have to be either, obviously this is not a good idea, but the Hadoop cluster can be pointed here, or you can spin up a Hadoop compute only cluster which doesn't hold any state to point to this. Okay, let's Hive Metastore and all that. Yeah, so Hive Metastore would have to be, using a SQL Galera replication or something like that. You will have to transfer the Metastore. Let's move on just to ensure that we cover the whole thing. Right. So how does this architecture of globally distributed data fit in with Hadoop? Right. ECS is a HCFS. Anybody knows what HCFS is? It's Hadoop compatible file system. It's basically a way in which Apache community has enabled other file systems to fit into Hadoop. By implementing a Java class called filesystem.java, you can make a client plugin and distribute it to your Hadoop cluster, which enables it to talk to other storage systems. We are vendor agnostic because we stick to the HDFS semantics. Basically, any vendor's Hadoop cluster could talk to our storage layer in a global manner. 2.7, I think I quickly mentioned that Kerberos enabled, and in the most recent release, Ambari can actually deploy the client jar that we need for work for the Hadoop cluster to talk to ECS. More on that is coming up. So a typical shared storage model looks like this. A Hadoop compute only cluster is on the customer side. By compute only, I mean everything that Hadoop has minus HDFS. Okay, yarn, MapReduce, Pig, Hive, HBase, everything, and the kitchen sink, but except HDFS. And now ECS will provide the storage backend, which acts like HDFS for you, right? This again indicates the polyglot feature of ECS. Now, this client library is the Java file system implementation. By putting in this special plugin jar in every Hadoop server node, the Hadoop applications can now talk to HDFS just like it was, standard direct attached storage. Moving further, the advantage, if we go back to the large bank we were talking about in the beginning, 27 Hadoop clusters they had, right? So that would mean that every one of those tenant clusters would have an HDFS layer here, siloing the data. Now with this kind of an architecture, every bucket in ECS can be set up as a file system for a Hadoop cluster. The same bucket can also be shared across two Hadoop clusters. So what that lets you do is your test cluster and your dev cluster can operate on the data, write their algorithms, and when it moves to production, it's seamless because the data is in the same place.
Does that mean that if we set a solution, we have found a workaround for the single point of error of the name node?
Yes, absolutely. Yeah. So that's where I appreciate the Hadoop community, right? So they provided an API interface which is so clean that it does not rely on the wire protocol compatibility, right? It does not require a Pig app or a Pig script to talk to the name node first. Pig just does an open, and how the open actually executes is the file system's prerogative, right? So if you implement your HDFS API set correctly, the entire Hadoop suite is supposed to work. And it does. I'm going to talk about that soon. So in the interest of time, I will skip through this slide. And I'll quickly talk about the Hortonworks certification. I mentioned in passing that any vendor distribution can talk to ECS storage system, right? But in particular, we have done an extra step with Hortonworks over the past year. We worked very closely with the Hortonworks engineering team, and we have gotten to a stage where both companies now certify each other's products as a certified solution. What that means is the HTTP 2.3 release, which is the Hortonworks Data Platform Release 2.3, is certified and validated to work against ECS 2.2, which is the latest release from ECS. So everything that we spoke about is not just a POC done in a lab, but this has been certified by both companies. So if you as customers face production issues with this setup, it'll be sorted out by both the companies. We also have this Ambari 2.2 integration where we deployed a new stack of Hadoop, which deploys a Hadoop cluster along with the client jars and configuration so that the Hadoop cluster, when it comes up, is ready to talk to a backend like ECS. Any question? Yeah.
You covered this a bit already, possibly, but is the ECS a hardware appliance? Is it software that runs?
Okay.
Or is it both?
Great question. So ECS has some characteristics like it's extreme dense and low overhead storage, right? So this product is available in both form factors. You can purchase a rack from ECS and wire it up, or you can bring your own hardware, install just the software from EMC and get this to run. But I want to put up some warnings there that the system has been built with some assumptions about how the disks work, what is the density before it does of the various calculations. So the hardware platform that you bring, DIY, it's vetted and certified before we can give some performance guarantees of the software.
About the ECS plugin,
Yeah.
how should we fit it? I mean, we've got our Hadoop compute nodes.
Right.
Where does it come?
Right.
Is it an OS? Is it a kernel plugin?
No. It's absolutely in the user space. So it's not a daemon, it's not a process, it doesn't take any memory or CPU or anything. It's a client library. It's just a jar file. It's placed in a well-known location, /user Hadoop, HDP, blah. It's placed in a standard location. Your core site XMLs of Hadoop are all told that, hey guys, if you see this URI, here is the client jar you have to talk to. And all your applications then talk to through the client jar. So it is not an OS kernel plugin. It is a user space jar file. And it's all installed and managed and configured by Ambari. So you don't have to do a SCP, Vim, any of those things.
So this is actually the ECS client he's talking about. The ECS server is completely separate.
You're talking about the picture with the black dots? Yeah.
The left,
Yeah. That's exactly what I'm talking about, yeah. We can talk offline and I can give you more details. I can show you the demo too. Yeah, I think now, all this is smoke and mirrors, you might think, but I think Vishruth will show you a live working demo which kind of demonstrates all these concepts.
All right, so I'm just going to go through a quick overview on what we are going to do in the demo. So this is the kind of problem that we have tried to solve here in this demo with ECS. So think of it as a network intrusion detection system where you might have your data centers across the country in US, California, and New York. That's fine. All right. So what we are trying to show here is that we have an enterprise with cross-country data centers, and they are trying to implement a system where they detect network intrusion into their networks, right? And the way they want to do it is they want to collect data from a network router in each of these sites, and then run some machine learning algorithms on the collected data. Now, the problem here is that there's huge amount of data collected across these two sites individually. So you can ignore this for a minute, but other than this, these two are kind of mirror images. Pretty much the same functionality is going on in both the sites, where the raw data from a network device is pushed into a Kafka queue. From that Kafka queue or Kafka topic, a Spark streaming job picks it up, does some enrichment of the data, and pushes it into ECS. The same thing happens on the other side. Now, we have two systems collecting data, and finally, that data, because this data is being persisted on ECS, it gets geo-replicated. And so the Spark batch job, which is sitting only on one side in New York, is able to talk with just one ECS in the New York site and be able to get the raw data, which has been uploaded from both the sites, because it can now rely on the strong consistency which ECS provides. So what it really means is that at the instance at which it hits ECS, it is guaranteed that it will see the data from its local site, obviously, as well as the data from the remote site. And once it processes the data and generates some models in a nightly job, it puts the models back on ECS. Now, the reason we want to put the models back on ECS is because not just the local site, but even the remote site needs to take advantage of these models. So once the models are put back into the system, again, the Spark streaming job pulls it out of the system, applies it to the real data that it gets, and generates alerts based on the models and whatever matches it gets of the model with the current real sampling of data. So here what we see is a typical dashboard of the ECS system. It just shows the high-level usage of the system in terms of the use space, the free space, how many nodes are in the system, how many disks are per node, and so on. This is just a typical ECS storage system in action. And this is one of the sites. The other site will have something similar because we are running ECS on both the nodes. The next thing we do is we want to set up a geo-replication policy. So as Nikhil mentioned that in ECS, you could have your data which is getting geo-replicated, as well as data which is not getting geo-replicated, depending on the class of storage, right? So the way we do that is we define something called a replication group. And in the replication group, we can then tell ECS that which sites the data belonging to that replication group should be replicated to. So in this case, a replication group called RG1 specifies that the data should go to these two sites, irrespective of which site you are using to ingest that data. The next thing is it gives you some information about the servers in each of the VDCs. It's just plain old IP address. The other thing to note here is that ECS at its heart is an unstructured storage engine, and it was really a object store. So all the data in ECS is organized in terms of objects, buckets, namespace, just like you will see in Amazon or OpenStack, right? Now, any Hadoop file system maps directly to an ECS bucket. So ECS does not have a limit on the number of buckets. It could span up to millions. And so you can have as many number of Hadoop file systems. Here we are going to create a Hadoop file system as an ECS bucket. But we also need to make sure that that file system or that ECS bucket, I think it's a bit blurry, but this is the bucket which we are going to use. And here it says the replication group for this bucket is RG1, which is the replication group we created so that the data in that group goes across both the sites. So this is some of the provisioning which the admin has to do before HDFS kicks in and starts running its jobs. Next, we are going to just look into the Ambari, which is a Hadoop compute cluster. Again, both the sites will have Hadoop compute clusters. We are just going to go on one of the sites, and we have deployed some applications on it, and a part of that is Kafka and MapReduce. Sorry, not MapReduce. Zookeeper is one of them. But primarily, we are going to use Kafka in this particular demo. So this is the interesting part of the demo where you really see the streaming jobs running. Let me remove this. OK. So basically, what you see here is the left side is simulation of site 1. The right side is the simulation of site 2. I'm sorry, but I think it's a bit difficult to read. So the upper boxes are simulating generation of data of a network device, which is just a Python script taking a 700 MB CSV file, which we got from the University of California website. This data is raw data, which any network device might emit. It has things like source and destination IP addresses, the transaction for that connection duration, and so on. And so what it does is it takes this data, enriches it, and spits it out into ECS on each of the sites. So this guy is spitting it out on his ECS. This Spark streaming job is spitting out the data on its own ECS. So this is site 1, and this is site 2. This was highlighted to show that both of them are connecting to different sites, but they are actually going to the same bucket, which is the same Hadoop file system. So even though they are going to different geographic locations, the data actually is going to the same bucket, which is getting geo-replicated in an active-active manner. The next thing we will go through is show you a peek into what actually we have done in terms of the raw data as well as some of the enhanced data. Yeah, go ahead.
What is the advantage of the ECS approach compared for such a situation using distributed hash tables?
You will use distributed hash table to do what?
This is like collecting network data and two different locations and then having it together. So did you think about distributed hash tables, or are you saying this is the approach and here are the advantages?
So the advantages here is, so again, when you are pushing the data out into the ECS system, they are not doing a WAN round trip at that time. It is an asynchronous geo-replication, right? The way it provides active-active is by doing an index replication or index lookup when it's required. ECS has a concept of object ownership and bucket ownership, and that is how we achieve that. So in comparison to a distributed hash table, this is beneficial because with distributed hash table, you will have to implement the active-active and strong consistency semantics on your layer. A distributed hash table will not do that for you, right? In this case, ECS does that for you. So all the consistency semantics, strong consistency, making sure that the transaction, once you acknowledge the user, it is persisted to the disk, and so on. Those kind of guarantees are provided by the engine, the ECS storage engine. So this is an example of the Spark streaming job, which we have, the Python script, which takes in the CSV, adds a couple of fields to it, and then pushes it out to a Kafka message queue. And then the Spark streaming job will take it out from the Kafka message queue, enrich it, In our case, enrichment is just a simple thing of adding two fields and putting something in. It's just for the sake of it. But in real world, you can have a pretty complicated enrichment example going on over there. So the enriched data is then put out to another Kafka queue, and from there, a Flume instance takes it out and puts it on ECS. So if I go to the original presentation, this is where we are. So it took it from here, put it in this Kafka queue, and then it's draining out into ECS. So this is an example of a message in the Kafka queue. Again, it's not really too edible, but in terms of enrichment, this is the only thing we did. We added the source and the destination bandwidth and created a total bytes kind of thing. Now, the next thing is to verify that the messages are actually going into the ECS. And the way we do that is we just go and look into the contents of the bucket that we are using. Now, we can go to any site and do that. Right now, we are doing this on site 1. But at the same time, during our live demo, we do it on site 2 in 2 concurrent windows, and you will see the same contents, which kind of proves the point for ECS being a strongly consistent system. So, yeah, basically, because we are a file system, all the file system commands will work as is. Spark batch job. So if you go back to the presentation, this is now taking action. So all the data has been moved over here from this side and have been moved over here from this side, and finally ECS does the replication. So this guy can pick it up and start generating models out of it. So while we are talking, the Spark streaming job is kicked in. Usually it takes a few hours for this kind of a job to run. And at the end of this job, it will create some models which it can run against the live data and push it back to ECS. So in real world applications, this would usually be run as a nightly job. And so all the samples which have been collected during that period of time or 1 day's worth of time are used by this machine learning algorithm to spit out models at the end of the day. So let me just pause it. This really is where the data gets stored on ECS. So ViperFS is just, we are using ECS as a supplemental file system in this Hadoop compute. Rep bucket 1 is the name of the bucket which we are using, and the rest of it is the name resolution which we use in the URL. So once this thing gets its job done, it will generate some models, and finally we'll just do an ls on the same bucket to make sure that the models which have been generated by the Spark job or the Spark batch job are stored back on the ECS system. So at this point, both the sites can start making use of this model. So at this point, the models generated by this is pushed here, and using ECS replication, they get pushed to the other side, and then the Spark streaming job on both the sides can start making use of those models. So the value of ECS here comes when you're generating models at the same time. You don't want to overwrite each other when you're generating it. If not models, then even when you're generating raw data from the same from 2 different sites, you don't really want to overwrite each other, which is what ECS manages by providing the consistency semantics. So in this particular demo, we went a step ahead and did some integration with the Zeppelin notebook. So what this really does is, at the end, when the alerts are generated, in this particular example, so coming back here, once the models are being consumed by the Spark streaming job, it will start generating alerts based on whatever alerts it finds from the real data. And here we went ahead and introduced another Kafka topic. So the alerts are thrown into the Kafka topic, and Zeppelin taps into those Kafka topics to give you a visual representation of how the alerts are generated on each of the sites. So it's a real-time update thing where it goes ahead and pulls data from those Kafka queues and segregates it by site. So this is site 1, this is site 2, and it kind of gives the information on how the alerts gets generated while the live traffic is going on.
So folks know what Zeppelin is, right?
Yeah. So this was sorry. Go ahead.
Now, it's an interactive notebook experience which lets you do exploratory analytics. So Zeppelin Server can let you instantiate what is called a notebook, which can be connected to a Hadoop cluster. And using interpreted language, you could start writing your analytics query right in the notebook. And it has very interesting features like sharing a notebook between data scientists. So 3 data scientists can collaborate on a data exploration product where they can pin some cells, tell each other about the information that they have discovered till now, etc. The Databricks cloud guys pioneered this experience, so it's pretty cool.
Okay, so yeah, so this is the final a state of the pipeline where you monitor the alerts on each of the sites using the Zeppelin. I mean, you can use any other tool you want. We just thought it would be interesting to use Zeppelin while it's being talked about right now. Okay, so do we have any more? Yeah.
For the data consumption, now let's say I have 5 different data lakes in different countries. My challenge is if I want to do cross data lake consumption, it is not possible if you have a cross join across countries. It is not from the performance perspective. Is it possible with your tool to have, let's say, that I get automatically in one place all data, while I have the other lakes had, let's say, just reduced to the local stuff? So that I can say, all right, I define one bucket in country X, everything is, and all the others have the local.
So wouldn't that give you a point of failure when country X's data center goes down?
The copy is in the other, so then you have...
Yeah, so that's what ECS avoids, right? So consider you have 4 sites, right? Now, we are trying to make sure that in your example, the way it will work is all 4 or all 3 have their local data, and the 4th one has its own local data plus the data of all 3, right? So the consumption of 4th site becomes very high. Chances are that your 4th site will get full a lot faster than the other 3 sites. And what you get in return is still a protection against 1 point of failure. You cannot protect against 2.2 failures in this case, right? Because if site 4 and site 3 goes down, your site 3 data is gone, right?
In other words,
so that is
replication is always bidirectional. It's not unidirectional. So you cannot say that I just want the data from here to go there but not come back.
yeah.
I think you guys should talk to the speaker of the previous speech just in this room.
Yes, I attended that, yeah.
Okay, because he was looking for a tool exactly like that to unify access to all local data, and it seems to me like the ECS solution is precisely that.
Yeah, I attended a part of that talk, so thank you.
Can you please get back to the first slide or the second slide? I just wanted to make sure, because we were talking about replication, this is one thing.
This one, I think this one. You're talking
Yeah,
about this one?
Slide, this one, perfect. I want to know exactly, to understand how does it work. We've got, can we put 2 ECS on the same data center?
So ECS is your data center. So think of it that way. This is one data center, right? On one data center, there have been customers who have put data centers next to each other in a building, right? The problem is that if the building loses power, both your data centers lose power at the same time.
Exactly. And the problem is if my rack is failover.
So within a data center, ECS makes sure that your failure domain, which is maybe your entire rack with 1 power supply, that going down does not affect your data. So we make sure that within a zone, we are aware of the failure domains. So that is irrespective of the geo distribution. Even if you have a single zone or a single site with ECS, one rack going down will not create a problem for you.
Okay. And the last question is about, there are some interesting things here, really. But do you have as a plan to develop ECS plugin to kernel, to system kernel? I mean, you've got a Hadoop plugin, but this would be quite quite interesting to have a plugin for a system so that I can also use it for Cassandra or whatever big data, NoSQL technology. Is it in your plan or not?
So Cassandra uses, you can use a file system on Cassandra, right? You can use a file system with Cassandra.
Yeah, with Cassandra, it's exactly as Hadoop. You've got your record storage and things like that.
So we have taken approaches like that for other systems, but not Cassandra. You know, Pivotal Hawk. It's like Impala. It's like Cloudera's Impala. So we have written a special plugin to get Pivotal Hawk SQL database to run on ECS. Similarly, we are working on getting Impala, Cloudera's Impala SQL service to run on ECS. Similarly, we should consider proposals like Cassandra and other NoSQL databases too. But right now, we haven't had too many asks from customers.
And in general, any tool or any component which communicates with the storage system using either NFS or S3 or OpenStack will work with ECS because ECS is fully compatible with those products. Yeah. Yeah. Sure. Yeah.
You had a question?
Just one. Do you have specific requirements on the connectivity between the sites?
So there is a band. I mean, see, the thing is, the slower this link is, the slower will be the async georeplication. And the slower the async georeplication is, if you just ignore the third site for now, right? Let's say you have two sites. Now, if this thing is really slow, then your chances of losing data on this site, let's say your ingestion is coming here, the chances of losing data increases, right? Because if you have ingested 10 GB and this link is so slow that we were only able to replicate 2 GB and you go down here, then you just lost that amount of data. There's nothing you can do around it, right? No system can get data out if your geo link is being slow.
Is it a hub and spoke replication or a hub by hub replication?
This is not hub by hub, so this will have a direct connection to this.
It's a star topology. It's not a star. Yeah, it's not it's fully connected mesh.
Yeah.
So within a location, do you store only erasure coded like packets, or
Yeah.
you store the original data as well?
No, so when the data is ingested, it's a three-way replication. In background, we do erasure coding, and then we have on top of that. So this is for a single site. Now, if you have 3 sites, we do something called XOR mechanism, which actually is intended to reduce your overhead for georeplication, at the same time tolerate failure of one site.
Okay, my real question is, so if you're not storing the data in an uncoded manner, then can you somehow provide data locality?
We can provide data locality. In fact, we are working towards that. The only thing is right now when we ship an appliance, it depends on how much memory you have on the appliance, and to reduce the cost, our appliances have only enough memory to run this. So if you bring your own DIY, kind of your own hardware, which has a huge amount of memory to be able to run the compute jobs, at the same time run the storage engine.
So I think
data locality in a manner that the computation goes down to the exact node.
Yeah.
So do you like decode on demand in this?
No, let me try to answer that. So I think data locality would make the most sense if Hadoop compute slots are also on the same set of servers that ECS is, right? So then you can place your Hadoop compute slot right where the block is. But the model here is that they are anyway across the network. So if you can tell Hadoop that, hey, my block B1 is on host H2, it doesn't help Hadoop because finally it has to go over the wire. So data locality, but absolutely makes sense if and when we decide to host Hadoop right inside these servers and not over the network. Make sense?
Yeah.
Yes.
If I understand it quite well, erasure coding is local on that site and not dispersed over.
So it's technically not dispersed across all the sites. We do some work around making sure that there are certain code fragments we ship. If we have a geo-replicator system, we try to ship certain code fragments so that we can recover in extreme cases after incurring a WAN round trip.
So, but the objects or the files are replicated as entities.
Yeah, so I mean, right, in a normal scenario, you would not need to go over WAN to fetch the object data. What might happen is you put an object over here, right, very next second someone try to read it over here. That might incur a WAN traffic because the async replication has not kicked in. But the subsequent reads, we would have cached it over here.
Actually, sorry, I was thinking we are 10 minutes over. Can we wrap it up so we can take questions offline? We are 10 minutes over. Can we do that? All right. So we just have to give out our raffle. So.
Up to you.
Okay. All right. So personally, I like the code questions on erasure coding the most and data locality because that is something that we grapple with on a day-to-day basis. Our customers always ask us, Hadoop was built with data locality in mind, that your data task trackers and your data nodes need to be on the same node. What happens here? So that is something we've grappled with quite a bit, and it hit home when he asked me that question. So I think, I know your name, please.
Marcel.
Hi. Thank you.
I'll ask another question. So I
No, you're done. You're done.
And we can.
Thank you.
So we'll be hanging around till the next.
No, we don't have a
speaker
next talk,
comes
so we
in.
have all the time. So
Yeah, so we'll be hanging out here. We can take questions now.
Wish you.